Hello everyone, my name is Xinyu from SGTU. Now I'm a visiting PhD student at TUM. My paper topic is Fourier basis guided diffusion for temporal interpolation of 4DMedical imaging. First, let's come to the background. Our task is to solve 4D temporal modeling on breathing-induced motions. To be specific, that is to generate intermediate frames with given starting and ending frames, just as what the figure illustrates. And that is consistent with the concept of video frame interpolation. So, can we directly adapt these frameworks from natural domain to the medical domain? The answer is no, because there are some gaps between these two domains, including the image noise, unstable breathing, the disturbance to temporal modeling due to patient movement, also the discrepancy on the motion type. So here comes the question, how can we devise a specialist VFI model for 4DMedical volumes? Existing medical VFI frameworks face a major limitation. They hypothesize that the motion from the starting frame to the ending frames is totally linear. But that's not realistic in clinical world. Instead, our model is based on the hypothesis that the motion is nonlinear and quasi-periodic. The motivation of our pipeline is as follows. The target is to minimize the difference between the predictions and ground truth of the intermediate frames. The final output is the devised model I. So for our proposed model, we are based on two motivations. The first motivation is we can decompose the breath-induced motions in the frequency domain. Specifically, the motions are quasi-periodic, which means that they can be represented with some motion basis with different frequencies. And that is very similar to the fact that each curve can be made up of sine and cosine waves. The second motivation is that the motion can be decomposed into two parts, including the general patterns and the case-specific variations. This is our methodology pipeline. And there are three stages. The first stage is VE pre-training to acquire motion patterns. And the core component is Fourier motion operator, FMO, which is aimed to extract motion basis in the frequency domain. So we conduct the FFT operation. Then, based on the motivation we mentioned above, we decompose the motion into the general and case-specific information. And here, the physiology motion priors is injected into the VE pre-training. And these general motion priors are totally learnable. The detailed structure of FMO is as follows. We can see that the two parts, including the physiology motion priors, which serve as phase information. For the case-specific information, it serves as a magnitude part, and we combine these two parts into the final Fourier basis. And the reconstructed special feature f hat is supplied with more temporal consistency information because we introduce the physiology motion priors. In stage 2, since inference, we only have 2 frames, the starting and ending frames. But in the stage 1, the input is a complete video sequence. So we need to adapt the Fourier basis extracted in stage 1. Thanks to the well-known general motion patterns in stage 1, we directly adopt it here, and it's frozen. So the difference is inputs. We transformed the previous video sequence into the masked video sequence with only 2 frames. And the extracted Fourier bases are the adapted results. Stage 3 is a conditional diffusion model for medical VFI, and the condition includes the coarsely reconstructed video from stage 2, also the adapted Fourier basis in stage 2. And the basis interaction operator is proposed to inject the conditional information into the diffusion model. We conduct experiments on 2 public data sets, ACDC cardiac and the 4D long. As shown in this figure, our model demonstrates the best vision perceptual performance on the LPIPS metric. Also, our model is based on the diffusion pipeline, so it cannot achieve pixel-wise reconstruction results. But as shown in this table, our model also maintains very satisfactory reconstruction performance. And this is qualitative visualizations on the most intermediate frames of each sequence. Our model can reveal the best fitting performance. For the ablation study, the first is we calculate the interpolation performance on the middlemost frames on ACDC cardiac. As shown in this table, you can see our model achieves the increase with a larger magnitudes on all these metrics compared to the performance on all the frames. The second ablation study is on the key components. You can see the general motion patterns set, the extracted Fourier basis B, and the coarsely reconstructed results V. They are all important to the final interpolation performance. Also, we give a visualization on the Fourier basis. We can see that the motion basis with different frequency, they can focus on different types of motion patterns. And that's the motivation of our model. Also, we give the temporal variation comparison. As shown in the table, our methods based on the nonlinear and the quasi-periodic motion hypothesis, which shows better temporal consistency compared to the classical linear-based interpolation model. As for the future work, we will focus on the motions with highly unstable breathing. That is quite complex, and that's all. Thanks a lot.